Okay, welcome to How to Get a Degree in Comparative Literature. Right place, right? Okay, maybe not. Okay, processing for better living. Nothing wrong with comparative literature, by the way. It's good to, the arts. We must balance ourselves. Okay, anyway, processing for better living. I'm Ashvin Thambyah. I'm from the Chemical and Materials Engineering Department. And hopefully you can get an idea of what a process engineer does. And the first thing I'll start with is World War I. Let's start from the beginning. World War I. One of the greatest killers in World War I was, what was it? Bullets, good. Infection. Infection. And this, anyway. But then along came Alexander Fleming and his discovery. Anybody not know about penicillin and the discovery of this antibiotic? So Alexander Fleming, he, in 1928, went for a holiday and left a dish near the window, and then this fungus, or fungi, you can say so many things about fungi, dad jokes and all. Anyway, there was not much room for the fungi. So anyway, this fungi got stressed by this bacteria and started releasing something that killed all the bacteria around it. So that's how they discovered that there was actually this substance that could kill bacteria. Okay? And they very creatively called it mold juice. It's a good thing we don't call that now. And by World War II, we were able to save lots and lots of lives. So how do you get that Petri dish to a wound and slam it on and save lives? It doesn't work that way. Okay? So this mold, when it produces this juice, it's a one-off thing. It's difficult to sustain. How do you get it purified? How do you get it into a little vial? It's viscous. When you in the old days, when you used to inject the first batch, it was painful as anything because it's so viscous. So you need to get it in to flow easily. All these challenges. So production ramped up so much that by the invasion of Normandy in June 1944, companies were producing 100 billion units of penicillin per month. Okay, that's 1944, and since 1928, matter of a very short time, they measured this. And that's all process engineering. So how do we get from a rudimentary plate of mold to 100 billion units of penicillin per month within a period of 10 years? And as I said before, the mold is as temperamental as an opera singer. Opera singers, are they temperamental? I don't know, but the yields are low, the isolation is difficult, the extraction is murder, the purification invites disaster, and the essay is unsatisfactory. People don't write like that anymore, but it's nice. So Pfizer, John Smith from the company made that statement and challenged, and the challenge was to actually make a system that allowed us to produce penicillin in large quantities. And I think the next slide shows a pioneer in that area, Margaret Hutchinson Russo from MIT. She developed the first commercial penicillin production plant. And she was a chemical engineer. And basically, it looks like this. Okay? Now, you're going to look at that and think, oh man, what's that all about? But after doing this degree, it'll look like this. Okay? But you will see that there are a lot of things that you'll learn about processes. For example, how do you apply the right amount of heat? The temperature sensitivity is a big thing. The pressure, controlling the fermentation process. And then deep fermentation, large batches. So creating a fermentation module that allows sparging, where you put in bubbles to allow all that material to sort of mix and blend. And extracting, drying out the material, getting the biomass. That's the product that you want to extract. The penicillin precipitate, okay, the good stuff. All that is what process engineers do. Okay? And you'll see that there's a lot of engineering, optimization, control systems, and with our materials engineering supplementation with our degree, you also learn a lot about materials. So these tanks, how they corrode, what can prevent corrosion, how can you build better, make better designed systems. Another example is steel. So of course, in the old days, you're making steel, and it used to take, for a ton of steel, take a couple of days. This chap here, he looks very stern. He looks like he could be a principal, a very strict principal that just doesn't allow climbing trees. But anyway, Henry Bessemer, he actually found a way to process steel such that in 20 to 40 minutes you can get the same amount that it would have taken two days. And that was crucial to getting some of the big projects on the road, like bridges. But, you know, big buildings, and that sort of spurred a lot of that. Another sort of, this guy looks a little bit more friendly. James Young, so he found, this is something else that process engineers do. We create value. Something that's useless and annoying, we make them useful, okay? Although my cat is still annoying, but I will find a use for her one day. So anyway, most farmers in the early 1800s saw seeping crude oil as a nuisance, okay? But this chap came along and found a way to convert that mineral into a useful type of oil to be a fuel, okay? And this was the start of something. So the mechanical engineers were making cars, for example, but the fuel is important. You can make a car, but it'll just look like this and not do anything. You need the fuel to let it move. So processing stuff became really important, and this is an old picture here showing how the early extraction of crude oil. Okay. And in the US, actually they were very inspired. A lot of these whiskey distillers were used for the oil refining. And you can see, you know, this little thing here. Look at that. Distillation. Okay? Fractional distillation. And this was the earliest oil refining process. You know, look at that. Distillation, not moonshine. Okay. So the ideas of processing, actually we just had our fourth year students start a little project on their own, nothing to do with course assessment, making beer in the lab, you know, their own brand of craft beer. So all these students, and yesterday we just tried it was fantastic. So they went in there, they sort of adjusted the gluten, you know, the sugars and everything, and they're gonna challenge and see who comes out the best tasting beer in our fourth year dinner. Anyway, so that's process engineering, okay? And then you have the huge fractional distillation that goes on. This can be up to 40 meters high. And essentially you get this oil and you study the oils. So it's not just about putting heat and raising the temperature and then getting all these products to come out. It's also about controlling that heat, controlling the pressure across the system, controlling about the mass transfer across the system. All of these things require a lot of fundamental knowledge in engineering that one study. So we actually study the properties of the material that we are processing and how they change phase, how they transfer in their state from a liquid to a gas, and then help to optimize some of these processes. So it's all this upscaling. Okay, from a small laboratory-based discovery to then upscale into something that's 10 stories high and producing for large masses. That's what we're all about. You can make a lot. You can make a CD. Everybody wants to make a CD, right, these days? Okay, maybe not. Okay, but plastics. Fish like them. No, that's a bad joke. Okay, too soon. Okay, so again, complex structures, and of course, you know, this is something that you learn, not just the process, this is diagrammatic, but of course the actual, you have visits to the plant, we take you out to the different Methanex, or previously we used to go to Marsden Refinery quite a bit, and you actually see hands-on how these things work. There's some examples of some of these large fractionation, distillation. Oh no, Okay, that's because it's a link to this. It will subside. It will. Patience. It's passing. Like Auckland rain, it is passing. Yes, okay. Yes. Next, milk. Okay, gone are the days where we get milk like this. Might be cheaper, but gone are the days. Okay, another example. Look, a happy milk person. When hats like this were in fashion. This is my favorite because, you know, they got the legs tied at the back, the cow can't go anywhere, and, you know, this is engineering. So anyway, it's with how do we get milk, and how does milk become like one of the greatest money-making thing for the country? So it's all about process engineering. Yes. And it's about transferring that raw product into something. So for example, Fonterra actually exports a lot of its product, and a lot of our graduates also work with Fonterra. And it's about turning that liquid, you're doing the spray drying, whether it's spray drying or whatever it is, to actually process it to a form that can actually be transported effectively, long shelf life. So this food engineering is part of process engineering, and that's what we do in our department. This is another example. And I think this is a good example of how materials engineering, so we are a chemical and materials engineering department, and you'll find in other chemical engineering departments around the world, and of course, and maybe I didn't mention this, process engineering is chemical engineering, okay? So we have this materials aspect, and for example, that comes in handy when, say, trying to find a solution to keeping milk from going bad, long shelf life, and you know, being able to transport it all around the world. So Tetra Pak, for example, is a material solution to increasing the shelf life of the product. This is a process engineer, okay? Anybody know what this animal is? Yes, also known as the civet cat. The civet cat. Why is the civet cat a process engineer? It processes coffee beans. So the civet cat eats these beans, and they come out, and apparently it's the best coffee in the world. I've tried it, you know, my taste buds are not that sensitive, but never mind. So the reason why I'm showing this is I have a colleague, a professor, who's actually trying to understand how these beans are processed in the biological system of this civet cat, and trying to see if that can be done in the lab. To make beans be processed in a way that we can get really nice tasting coffee. Although when I visited Indonesia and I talked to the chap that was selling had these civet cats and they let them out and choose. He said it's not in the processing, it's the way the civet cat chooses the beans. But I don't know. Why am I showing you crab shells? Well, maybe because I'm hungry, but crab shells, okay, you have shells like that, you have mussel shells. When you see these shells, what do you do with them? You throw it away, right? So they're waste. So a process engineer tries to use that waste and make some value out of it. So we have people in our department that's converting these, oh, look at that. We have people in the green-lipped mussel in New Zealand, best in the world, isn't it? Okay. We have people that are converting the shell into useful products. So in our department, there's one group that's converting mussel shells into hydroxyapatite. What's hydroxyapatite? Apatite here, nothing to do with mussel shells. Apatite. Okay, anyway, it's a mineral that is found in bone. Okay? So that hydroxyapatite has got value. If you try and buy it from industry, it's very expensive. But here, if you can convert it and get some good pure hydroxyapatite, it's a good use of that waste, and it adds value. So there's a lot of uses for the different components of waste material, and that's what we look for. And we try to actually get some value. Yes. So, for example, even the bones of, so when a cow gives birth, it's a male or a female, correct? We all know that. The females go on to give milk. The males go on to live to about 2 years old, and then they're slaughtered for their beef. Yep, such is life. It's not equity in the cow world, you know. And the bones get chucked away. It goes into making fertilizer and stuff. But what if we can add more value? So there's also projects going on in our department where we're taking that bone and processing it to make bone grafts that can be put to replace lost bone in humans. Okay, and this is a big industry actually, and for tissue engineering. Okay, so what is process engineering about? It's about learning how to solve problems in everyday living by creating and developing innovative solutions that provide optimum use of the world's limited resources. I think this is important because I showed some of these old examples. So if we think about how industry has maybe gone a bit too far, the environment has been affected. So while one can argue that you process engineers just messed up the whole world, but we are the solution as well. Okay? So the only way to get out of that, so we have come a long way, we've eradicated a lot of poverty around the world, but there's now a challenge to actually make things better, and that falls on the engineer now, to turn things around. So limited resources, we want to work with limited resources as opposed to trying to exploit everything. So that's something that we try and teach our students. It's about understanding processes from the minute to large scale and making things run more smoothly, efficiently, and cost-effective. It's about adding value to products. So a diverse range of applications to medicine, energy, food, water, manufacturing, environmental health and safety, biotechnology, mining, exploration, and many others. Okay? So in our department, you'll see these areas in which we tend to be teaching about. So materials engineering, heat and mass transfer, again, coming back to that, controlling of temperature and things like that, properties of fluids, thermodynamics and kinetics. Who likes thermodynamics over here? High school students. You probably wouldn't have got, but some of you may have read about entropy and all that kind of stuff. So it's quite interesting stuff actually. Materials performance, separation processes, unit operations like that distillation column, advanced materials, chemical and materials design. Here design refers to designing a solution to a problem. That's where the word design comes, as opposed to let's design a nice pair of pants. Although that is design. Okay, so process control. This is where you have a process and there are different parts to it. So you may have the pressure is controlled in this region over here, then the temperature over here. And within that pressure, you have all these different valves. All of this is now linked to software engineering as well. So everything's controlled by software. So you can actually go in there and do coding to change processes, to optimize processes. So that's an example of that process control. A lot of modeling there. Process economics. So increasingly, we're looking at a systems approach to solving the problems that include cost effectiveness and looking at the whole supply chain and how things cost at one end and the cost of putting in a new process or taking it out. So looking at the economics is also important. And you will learn about nanotechnology. So at the 4th year, you actually do a research project, an independent research project, and it will be in one of these areas. Nanotechnology, energy and the environment, food science and process engineering, high temperature process engineering materials, food and bioproduct process, separation and reaction engineering, green process engineering, surface and material science, and biomaterials. So we have quite a diverse range of research focus in our department. So you can find this in the website, and I think the main thing to note here is IChemE. So that is the Institute of Chemical Engineers, that's in the UK. So our degree is accredited to that body that has an oversight on all the chemical engineers in the Commonwealth. Which means that if you get this degree, it is transferable to, it's recognized in all these other countries that are part of that IChemE accreditation. And it's also a pathway to get to be a chartered engineer or one of those professional engineers if you're doing some consultancy type work. Okay, what is this? Updated data. Okay, so the challenge for us is in water, energy, food, and well-being, and that's one of the areas that we are trying to gear our students to trying to solve some problems in. And here, speaking about the report, IChemE's, chemical engineering remains central to the delivery of sustainable water, energy, food, and well-being, and the breadth of the chemical engineering discipline. So that puts the profession in a unique position. So really, if you want to make a difference, this is one to the world and how we use our resources. This is one area, one degree that you can take to try and equip you to meet those challenges. Now about employability and salaries. I think this is quite important as well. Students and parents also know that, okay, this is just saying this, great. Recent growth trends and long-term demand for chemical engineering remains robust. Okay. Why not ChemEng? This is something else. Okay. This is just, if you Google why not ChemEng, you can find a lot of information if you want to carry on the inquiry about what this is about. Okay, so just Google why not ChemEng. Career services here in New Zealand, outlook good. The outlook for chemical engineers is good, and the number of people employed in this occupation expected to grow moderately over the next 2 years. Increased demand for chemical engineers. This one, chemical engineer job opportunities. In Maori, your Mataru Matu. Chemical engineers design, okay, so it looks good. This is, I think, from which year? So I got something here that sort of, this is current. Let's go to the current. What do they say? I'm hoping it's still good. Yes, it's still good. Okay. So, salaries. Okay, some indications. So, chemical engineers work as petroleum engineers, and then, of course, as chemical engineers as well. Mining, in the mining industry. So these are just some salary indicators. This is another salary indicator over here. Chemical engineering. This is US. This is interesting. So this future in tech, chemical and process engineering, and they talk about what they do. What I found interesting was, of all these students here, Ian Riddick, Brooke Clark, Sarah Holmes, Nicholas Sue, Owen Miller, and Chris Horan were all from our department. So I thought that was interesting. Forbes says that the 5 college degrees with the biggest salaries, petroleum engineering. So our chemical engineers work in the petroleum and gas industry. Chemical engineering, because in the US they have petroleum engineering, and then of course in the mining. So our students tend to do quite well, and just more stats. Okay, you get the idea. So some famous chemical engineers: Arthur Fry, post-it note, something as simple, chemical engineer. This is interesting because a lot of our chemical engineers also opt to work in the commercial sector. And so we have people, because they're seen as problem solvers of diverse problems and not just technical. So they work for banks and so there's a very Gore-Tex. So again, the materials aspect is very important, and that's something that we include in our chemical engineering degree. Basic science as well. Our chemical engineers are also equipped to do very high-level basic science research and win Nobel Prizes. This is our most famous chemical engineer, Cindy Crawford. But she dropped out. So if you want to do well in the modeling world, get into chemical engineering and drop out. That's the message. So we are very, in terms of all the engineering departments in the faculty, we are proud to say that we have quite a good balance in the gender. So we have, last year we were 50-50, and this year we could be a little bit more. I'm not sure of the actual numbers. So that's really good. So girls, yeah. Oh, by the way, guys. It's a very collegial department, so we have a rather smallish group, so we have competitions, and sometimes we have really good competitions. Paintball, that was fun, and we won. Lecturers. So join us, and if you have any questions, please, I'm here to take some questions, but we also have a booth over there. Okay, thank you. So questions, any questions? Any questions? Anything? Yes, one back there. Yes, go ahead. Question.
Thank you for your presentation. It's lovely.
My pleasure.
And I want to know in the university, is any internship arrangement for students?
An excellent question. So, with our degrees, all our engineering degrees, the students have to do 800 hours of practical work. That means, so 800, what is 800 hours? It's usually done during a summer period. During the summer period, there's like, say, 10 weeks you choose, and you work 40 hours a week, that's 400 hours. So one summer, you cover 400 hours in which you might work in some company, in some laboratory. So we have industry engagement representatives within the department. There's an academic in charge of that, as well as within the faculty that tries to arrange industry engagement for the students where they can apply for these internships in these companies. Quite a number of our students, for example, if they go and do an internship in New Zealand Steel, the people there like them, they get that exposure, then they carry on to work for them. So yes, we encourage our students to actually have that industry connection. Our department has actually got an advisory board that consists of industry members that also tries to build that link between academics and industry. Thank you. Oh, okay. Good answer. Yeah.
How many undergraduates need to
For chemical engineering or total? Okay, so we take in about 80, so the first year is common. 1,000 students go into the first year. And then from the first year, 80 students go into chemical and materials engineering. So the 80 to 85, not that 80, why did I say 80 to 85 like it mattered? Okay, 80 students. So it's quite competitive to get in. And it's decided more like a GPA scale. So if your GPA in the first year, if your grades in the first year are really good, you get your first choice right away. Yeah. Yes?
Are there any subject requirements or recommendations?
Nothing. So whatever you need to get into first year is all you need. So once you're in first year, you do that common first year. It's all about doing well in first year. So there's no special requirement before coming into chemical engineering. Good question. It's all about getting into that first year and doing well in that first year. Once you get into the first year, forget about high school. Think about just doing well in the first year. And usually the first year is, you sort of get, oh wow, I'm free. But that's where the discipline has to come in. And just do well in the first year, and then after, once you get into Chem Mat, you can sort of, yay, I'm free. Maybe not. Okay, you still have to work hard. Yes?
How often are we in class like a week?
That's a very good question. Now, we would like everybody to be in class often. Okay, so roughly, we have 4 subjects per semester with 4 hours of class time each subject. That sort of gives you about 16 hours maybe a week. And then plus some lab time, maybe, and 20. Yeah, so it's quite, the lectures are 1 hour long, and the labs are about 2 hours long. So it's a full-time course, yeah, for sure. But there are students that work part-time, and they try and manage those hours. And especially, I think the first and second year, the best is to focus on getting a grip into the degree, and then start to see how you manage your time. And then, if you need to do part-time work, to then manage those hours for part-time work a little later, once you get an idea of, yeah. Because it's so important to do well in that first year, and then sort of to get a good foothold in that second year. Yeah. Yes?
Do chemical engineers travel a lot?
That's a good question. You know, it all depends on which company you go to. Now, there are a lot of chemical engineers that graduate from our program that choose to work overseas. So working in Australia is quite common for a lot of our graduates. Whether they travel a lot depends. So there's one student that's working for Becca, and although she's a fresh grad, she's working in a team that provides consultation. So she travels around New Zealand and Australia a little bit, and sometimes to Singapore. So yeah, it depends on which company you're going to work in. Okay, so we have a booth in the display if you haven't been out there yet, and there are more people to answer your question. Thank you for coming, and enjoy the rest of the day. Thanks.